everybody, and welcome back to this video and a second lecture on my DSA course, means Data Structures and Algorithms Mastery course. And in this lecture I'm going to talk about time complexity analysis we'll get and how we can use them. And because instructors are only drawing the graph, they're just talking about the conditions and they're just one. But I'll make sure that I'll make you understand each and every concept in an easy way. Okay, so let's start with this video, and first of all let's talk about why do we care about time complexity. Actually, why do we care? Why do we need time complexity? So let's talk about only 2-3 minutes onto that. That's why do we care? The reason why I care is, let's say you have given a lot of algorithms. You have given let's say in sorting algorithms you have a selection sort, and you have a merge sort. Okay, so there are a lot of algorithms, but let's take for example, you are given two algorithms, merge sort and selection sort. So here you can see that a selection sort, if you could take a 10 million example, then this will not even go to 1 million, but a merge sort will go to 1 million, and in very less seconds, less time, and it will take more time to consume. So for comparing the algorithms, we have to check whether the time of the algorithms, I will compare with the time basis on the number of input. So for 10 million input, it will take less time, it will take a more time, or it will never converge to that. Okay, so that's why we care about time complexity analysis. So I hope that you got better intuition about what I'm going to talk about. Okay, so for actually doing this kind of comparison for time complexity analysis, we have asymptotic notation. So this is there are three types of asymptotic notation. The first one is a big O notation, The second one is omega notation, and then we have theta notation. So these are our asymptotic notation that we will talk about, and we will end of this chapter, which is a time complexity analysis. Okay, so let's start doing in a fast way. So first of all, let me clear all those kind of stuffs. So I will put a green color here. So let's start talking about asymptotic notations. So I will give it a heading. The first asymptotic notation is a big O notation. So this is my heading. So what we have to do, we are given a function f of n, and n here is the number of input, or a size of input, and we have to find the big O of g of n. And this is the upper bound. And again, you might be very confused like other instructors, so just wait. So we have to find the big, so f of n should be the big O of g of n. So this is the upper bound. So for satisfying this condition that f of n is big O of g of n, let's define the things. So for a big O of g of n, for making this condition true, for big O of g of n, there exists there exists a constant c, which is a constant. There exists a constant c and n naught. You can n subscript 0, but let's notice the n naught. And the condition there exists constant and n naught. The condition to satisfy is the f of n, which is our number of input, should be smaller than or equals to our favorite g of n, which is an algorithm. okay, and f of n should be the smaller than or equals to 0. So this is the condition this for big O should satisfy. So only we have to satisfy this condition to make this true. And also one more condition is that n should be the greater than or equals to n naught. So this is my another condition. So for the f of n equals to big of g of n if and only if these conditions are satisfied. Okay, so this is how all it works, and this is the upper bound. It simply means that a g of n would be the greater and the f of n would be the smaller than g of n in graph. So let's take a look at a graphical representation of a big O of notation. Okay, so we'll go here till now. Okay, so I will make an x, y in plane. So this is my, and here we have a number of input or a size of the input, so I will give it a name n, and this is my the rate of growth, or we can think of it as a time. Okay, so both are the same, but the rate of growth is something kind of a good practice that I have explained you about. The rate of growth is a increase in a running time, or a decrease in a running time is called a rate of growth, but a time is also a good example. Okay, so let's plot f of n. So first of all, let's plot f of n. So f of n, let's say it looks something like quadratic function, and let's say we have a g of n which is something like this. Okay, so this is, oops, let's give it a green color, and a g of n should be the greater than f of n. Okay, so this is f of n, and you can see here that g of n is greater than f of n. So it is from seeing the graph, you can see that f of n is the big O of g of n. The reason why, first of all, the satisfy the condition because the g of n is greater than f of n, and that's what the condition is here, that f of n should be smaller than and g of n should be greater than f of n. Okay, and one more condition is that the n should be the greater than or equals to n naught. So let's take this as n naught, and we are good to go, and you can see here that n is greater than n naught. Okay, so pretty much easy for understanding the big O of g of n or big O notation. The only thing we have to do in asymptotic notation is only we have to satisfy this condition and we are done. Okay, and we can simply write a big O of g of n. So let's see what questions come in big O of g of n. And again, you don't have to write anything. All the things are already been written in as a notes. You will be getting as a PDF in the description down box below. Okay, so let's type a question and find the upper bound. Find the upper bound of f of n. Of f of n. Here is my question: 5n squared plus 2n plus 1. Okay, so this is my question. And I have not solved it, I've only solved it with other purpose. So this is your question, and what you have to do, okay, so what you have to do, you have to find the upper bound, means a big O of g of n. So f of n, so the big O of g of n, if and only if it satisfies the condition that f of n is smaller than c times the g of n. Okay, and f of n should be smaller than or equals to 0. So if we put, let's say f of n is, let's say g of n. Now how do we calculate the g of n? For calculating the g of n, there are two steps. The first step is that you terminate the lower terms, and the second one is that we remove the coefficient of the highest term. We remove the coefficient. So this is how all it works, and in this case the lower terms are this and this is the highest term, so we remove the coefficient, so we are left with n squared. So g of n is n squared. Okay, so what c would be taken and n naught would be taken, so it satisfies the condition, this condition. So for satisfying the condition with the c equals to 8, I can think of as 8, and n naught equals to, let's say, 1, we can satisfy the condition, because O of f of n should be the smaller than or equals to 8 times the n square, and if you put any of the two, let's say 2 here, then 8 times the 2 squared, always 2 is smaller than this, then they satisfy the condition, and we can say, so how do we write the answer? So we can write f of n equals to big O of g of n, big O of g of n, if and only if c equals to 5. It can be any solution, but we assume that this, if c equals to 8, we can think of it as 8, or it's been 5, and anything you want, but it should satisfy the condition, and n not equals to 1. With this, two constants. Okay, so this is how all the big O notation works. So I hope that you got better intuition about the big O notation. There is a lot of questions to practice, and all the solutions will be provided later on. We'll be given a sheet about a practice solutions or practice sheets. Okay, so this is how all the things works. So now let's talk about a second type of notation, which is omega notation. So let me clear this. So now let's talk about omega notation. Okay, so the second notation is omega O notation. In this case, the sign of the f of n, and n here is the number of input, n here is the size, let's say size of the input, is the sign here is not something kind of a pi. So this is a g of n. And how do we calculate the g of n? We terminate the lower order terms, and then we take out the coefficient. Okay, you will get a notes, and at the last page, just try to take a look at the notes after this session. Okay, so this is the kind of a sign for indicating that this is the omega of a g of n. Okay, so for satisfying this condition, for the omega of g of n, there for f of n, there exists a constant c1. You will be getting in a note, so I have to not write in more detail. You will be getting, so no worries. So there is a constant c1 and n naught. Let's say c and n naught, and here this is little bit opposite of big O notation. Here the c times the g of n is smaller than f of n. Or in other words we can say f of n is greater than or equals to c times the g of n, and again the f of n should be smaller than or equals to 0. And again we can say the n here is smaller than or equals to n naught. So it is little bit opposite. In the big O notation it should be smaller, but in omega O notation it should be bigger than the c times the g of n. So that's why this is called a lower bound. Okay, so let's see the graphical representation. So how do we graphically represent this? So again we have our favorite x and y plane. So I will put here x and y plane. Okay, and a favorite my green color, and I will draw a f of n. So this is my f of n, and this is my c times the g of n. So I will write the c times the g of n, and you can see here that c times g of n is smaller, so it satisfies the condition. So we can say f of n is the omega of g of n. Okay, and again you can take this as a n naught, this as a n, this as a rate of growth or time. Okay, so we satisfy the condition and we are good to go. Okay, so let's see one example indicating this. So here is my example. Find the lower bound. Lower bound. Again the same question of f of n equals to 5n squared plus 2n plus 1. Okay, so you have to find now here the lower bound. For finding a lower bound, for finding a g of n, then we get a 9n square. It's simply because we terminate these all and we are good to go. Okay, so here g of n. So for satisfying the condition, it will be the g of n, and it should satisfy for this. It should satisfy a condition called f of n should be the greater than or equals to c times the g of n, and f of n should be smaller than or equals to 0, and n here should be smaller than greater than or equals to n naught. So for satisfying the condition, we can take c as a little bit more crunchy, like c equals to 5. So we can take c equals to 5 and n naught equals to 0. Okay, so it satisfy the condition with these values. So you can take any values which satisfy the condition, pull out there, and you're good to go. So how do we write the answer? So we can say the f of n should be this of g of n if and only with c equals to 5 and n naught equals to 0. So this is how all this works about theta notation and a big O notation, okay, and omega notation. Okay, so we have talked about more in detail about a big O, omega. Now it's time for talking about a last notation, which is a theta notation. Okay, so let's clear the both and then I will come back. So now let's talk about a theta notation. So there is a third type of one last notation, which is a very useful notation, which is a theta notation. And this is also called notation and order function. Order function. Okay? So it is a very useful function. You will see a lot that if the upper bound and the lower bound are same, then the theta notation will be also same. Otherwise, no. Okay, no. So this is the thing that is very easily understandable. Okay, so this is how the simple kind of thing. But for theta notation for f of n, so the theta, sorry, it should be I've written omega. So it's a theta of a g of n. So for satisfying this condition, there exists f of n, there exists c1, c2 and n naught. These are the constants, and the c1 would be the lower bound. So c1 times the g of n should be smaller than or equals to f of n, and f of n should be smaller than or equals to c2 times the g of n, and this is the condition. And here you can see we got a lower bound, and here we got a higher bound. Okay, so upper bound. Okay, so this is the condition that we should satisfy to say this f of n is the theta of g of n. So let's see how we can represent it on a graph. For representing it on a graph, so let's make a simple kind of x and y. So this is my x and y, and let's say here we are given a time, and here we are given a number of inputs. So here let's draw an f of n. So this is my f of n, this is my f of n. Now let's draw a c1. So let's draw a c1, and c1 is lower bound, so this would be something kind of this. So this is c1 times the g of n. This is a lower bound, and this the c2 would be the upper bound. Okay, so c2 would be the upper bound. Okay, so this is how all it works. This has satisfied the condition that a c1 times the g of n should be smaller than or equals to f of n, and f of n is smaller than or equals to c2 times the g of n. And this is how all it works. And let's solve one question, and then we'll wrap up this video. Okay, so find the order function. Find the order function of f of n equals to 5n square. Again, the same question, 2n plus 1. So here g of n equals to, we can terminate this, like let's say we terminate these all, and we terminate n square. So you can put, I will give you the task here. So put a c1 whatever, c2 whatever, and not whatever, so that it satisfies this condition, so that it satisfies the condition, and we get a theta g of n. What you have to do, you have to put the values of c1, c2, and n0 and for satisfying the condition, and just try it out. Just pull out the input and pull out the two, whatever the input is, and check the condition whether it is true or false, and then on the basis of that, just do that. Okay, so this is a task for this video, and I hope that you got better intuition about a big O, theta, and all those kind of stuffs. Okay, so let's talk about some rule cases here. The rule case for calculating a g of n is we are terminating the lower order terms, and then we are terminating the coefficient. Okay, so this is how all it works, and I hope that you got better intuition about what I've said till now, and you will be carrying up to the next video. The notes is here, and you will be getting the same notes. We'll be providing you the PDF, and you will be getting the notes. So thank you for seeing this video, and in the next video we'll talk about some kind of recursions and backtracking, and then we will move on. Okay, so that's it for this video. I'll be catching up on the next video. Till then, bye bye.